Welcome to my presentation. My name is Stephan Schuler, and I'm a research associate at the University of Applied Sciences, Upper Austria, Campus Hagenberg. And today I'm going to present to you a textile-based capacitive pressure and shear force sensor. So the motivation behind this sensor was the following. Topics like data acquisition and performance measurement in sports are currently high areas of interest. For example, with smartwatches, you get vital parameters of ones or power meters in bicycle cranks, smart socks for gait analysis, and many more topics you can think of. And if we look more closely into force measurement systems, they consist mainly of string gauge systems, which are good, obviously good for the performance measurement in bicycle cranks, but bad for evaluation in other sport areas, like if you have in running shoes to performance analysis of the runner, or if you think of cross-country skiing sticks, cross-country skiing sticks, where you have to put it in the belt of the skiing stick to measure the performance. So our idea was to the capacitive textile pressure shear force sensor. The advantage here is we have a small form factor. It's quite easy to produce, and it's also directly wearable on the human body. So we used a similar approach as in the related work here, which use copper-tin-coated textiles as electrodes, but our textile electrodes are fabricated with an automatically machine. So, short to the working principle, the sensor consists of 5 electrodes. We have 4 sensing electrodes, marked with C1, C2, C3, and C4, and 1 ground electrode above. So the overlapping area between ground electrode and the sensing electrode with the spacing in between forms a capacitor. If you move by force to it, change in capacitance is measurable, and also the direction is measurable of the force. So our fabrication of the sensor, we used silver-coated polyester hybrid yarns, which consist of silver-coated yarns and many polyester yarns. They have a specific resistance of 150 ohm per meter. And as I already mentioned, are fabricated with an automatic embroidery machine. As you can see in the figure, the top and bottom of the 4 individual electrodes, the sensing electrodes, and the ground electrode. The next step was then to sustain the connectivity for the electrode. So we applied the same yarn directly into the textile and connected them to the metallic press studs. Then the next step was to make the capacitor with the spacing in between. So we put the 4 electrodes on the silicone rubber in it. Don't resist it, and put another layer on top with the ground electrode and waited until it hardened out. So we had a silicone rubber with a short hardness of ACUC, and the spacing in between the electrodes was around 1 millimeter. Yeah. So for the picture of the data acquisition of the sensor here, which is directly connected to capacitance to inductance, capacitance to digital converter, which then translates the data over I2C to a development from STM32 and over to laptop PC to visualize the data. With the sensor now in hand, we are tested the sensor with our test sense system, which consists of a step limiter, a driving sled, a force sensor, a mounting sled, the test object itself, and the base of the test unit. In the picture on the right, you see the clamping sensor with the cables and ready to be tested. So it's two tests. So the sensor is clamped into the test rig, and we apply forces for about a duration of 24 hours. As you can see on the right, the force is applied, and the capacitance change according to the forces. If the capacitances, if the electrodes increase the capacitance, and if the electrodes decrease the capacitance, which is in accordance to the theory. So this is as mentioned for 24 hours, and then the sensor is rotated by 90 degrees on the vertical axis. So the capacitance value is increased on two electrodes, and the electrode values decrease respective electrode. So it is possible to detect the action of force. Force. General test values you will see in this table. The first range is from 12 Newton to 16 Newton per test cycle. So the change in direction of the sensing electrodes. So we tend to detect the direction of the force. So according to the data of 24-hour tests, we try to estimate the drift in the capacitance value. So how reproducible will be such a sensor in this scenario? It's quite black because the slope of the trend of the slope is quite small. So you can see it's 6 seconds. 24 hours. Seem to reduce that much, but not to experience so as applications I will find out it seems with the dielectric layer. So when on the sun, found particular for application for the electrodes, which gives promising results for flash research. As already mentioned, forces were possible to detect in northern direction. Sensor was limited, with small form factor suitable for future applications and on the human body. So, as I mentioned, usage of other dielectrics, extract the sensor, so it's not quite also material. So if you have to small example, changing the right force. Interesting. For example, systems which also forces with shear forces. So this from my side, I want to attribute